Okay, guys, welcome back. Chapter 7, Lesson 3. We're going to discuss objectives for today, relate the PES or the photoelectron spectroscopy, the photoelectric effect. We're going to kind of demonstrate and show you some graphs of this information and data and how it's related to electron configurations. It's awesome. It's really something we should have shown you guys in pre-AP, but it wasn't necessary. But you'll love it. It gives a great explanation for determining, or evidence for anyway, electron configuration and position of electrons and atoms. We'll use that data from the PES to confirm those valence electrons, as well as the core electrons and where they're located, some of them. And we're going to talk about Coulomb's law. We did already a little bit in class at school, but we're going to do it here for you guys and describe the way that it dictates the way not just electrons in attraction to the nucleus, but objects actually attract to one another based on their charge and the distance between them. All right, so let's get started. We'll talk about some of the trends too. Oh, wrong computer. Okay, so photoelectric effect I discussed with you guys in lesson 1. But the photoelectric effect is determined by the frequency of light that's actually shown on a metal or an object. When it does at a certain frequency, finally expel an electron at that threshold frequency, that electron will be, expelled from the atom with a certain amount of energy. What we find is the more energy that we add, the different frequencies of energy that we add, which is proportional to its energy, more electrons will be lost by that atom. And so by doing that, by increasing that energy frequency that we're giving to it, we can actually determine how much energy each of those electrons needs in order to be expelled, which is the same amount of energy that they're being held with. Once you overtake that, it loses the electron. But we can see which electrons are being lost and what their distance or position or energy level is relative to the nucleus of the atom. So it's awesome. And to do this, we use something called photoelectron spectroscopy. So it uses that energy from the electrons that are emitted to kind of tell us what their position or distance is from the nucleus. Quite awesome. And how many electrons there are. Okay, so when a certain light of frequency, like I said before, shines on there and you breach the threshold frequency, electrons are going to be emitted from that atom. Photons for photoelectron spectroscopy are used from ultraviolet and X-ray to have those electrons actually leave the atom. And so what I'm going to show you are some of those graphs here in a second after I describe this. So Coulomb's law, we're going to use a lot. Really teach you guys this in pre-AP, but whatever. They do a great deal with Coulomb's law in physics. Not only Coulomb's law used here, but it was the universal law of gravitation and others. But essentially what we have for us is this Q and this Q represent two different charges. Okay, so say the nucleus and an electron, or say a cation and an anion. And then oppositely charged, they would attract to one another. If they were the same charge, they would repel. This F over here on the left would represent the force of attraction or repulsion that is caused by those two charged objects or charged species. Down here on the bottom, that's the eraser. Down here on the bottom is the distance between them. We say the radial distance because when you talk about a nucleus and an electron, it goes from the nucleus to the electron. That would be a radial distance. But in truth, it's just, in truth, it's just the distance between those two charged species. So if it were a cation and an anion, it would be the distance between those two charged atoms or ions. So that's what those mean. The K is a constant for what you're working with, but you don't need to worry necessarily about the K value unless you were given it. But we really want to just use Coulomb's law to describe the behavior that we're seeing rather than doing straight up calculations of what that force is. All right, so PES. So what is PES? In a PES graph, like the one or images that you're seeing down here on the bottom, or down here at the bottom for hydrogen, it has two axes. The axis on the bottom, the x-axis, is the amount of energy that you're giving to that atom. So we're shining a light or energy on that atom or on that metal, or in this case, hydrogen, giving it energy, and then seeing where that electron is expelled, how much energy it took for it to be expelled and cause it to be charged. So the electrons that are actually closer to the nucleus are going to have that denominator of Coulomb's law. If I kind of scroll up real quick, the denominator of Coulomb's law is going to be really, really small. If the denominator is very small, so here, I do this with my kids, and I apologize, but if I write my K and my Q here, Q2, and I say my radius is really, really small, well, then my force is going to be really, really big, right? And so the hydrogen atom doesn't have a very large distance from the nucleus, that single proton, to that one electron. Whereas something that's far down on the periodic table, energy level 3, 4, 5, 6, and so forth, you would have much larger radius. And if you have a much larger radius in the denominator, there is a much lower force, a much smaller force of attraction of that nucleus for that electron. Okay, even though there are more protons in the nucleus, because it's so far away, it's really not going to have a very tight hold on it. And so it wouldn't take as much energy to have that electron be released by the atom. So cool. So in these graphs on the bottom, like I said, there's energy. And so I'm going to draw this, and this is really not kind of how it's really supposed to be done, but I'm doing it anyway, is that where you see that large energy value, that gets kind of really close to the nucleus. It takes a ton of energy in order to remove that electron. So I'm going to draw it here. I'm sorry, I'm apologizing, but I'm going to say that's the nucleus. And out here is that first electron. And how much energy it took is going to be, in this case, it's 1 millijoule per mole. And if you look over on the y-axis, this tells you kind of the number of electrons that are present, up, down. And this is going to a peak where it's 1. So that would be expulsion of the single electron on hydrogen requires a little bit more than 1 millijoule per mole. So where this really gets interesting is when you have elements that have multiple energy levels and sublevels, and we're looking at several different energy values for those electrons to be expelled, and it's kind of cool. But if you think of the very largest energy being kind of the nucleus, you're going to read your electron configurations in that direction. I'll do some more to kind of show you. The axis on the bottom, this is weird, the axis on the bottom can be flipped. Instead of going from a high number like we are here, 1,000 to 0.1, it could start at 0 and work its way across the other direction. In that case, your nucleus would be on the other side, and you would read the electron configuration in the opposite direction. I'll show you some of those examples, and none of these PEF graphs or charts, whatever you want to call them, are the same. They're all a little bit different. The first ones I'm going to show you for each element are, of course, identical. They're set up the same way, but we'll do some practice at the end where they're not quite the same. So that's hydrogen. If I go and I look at, say, helium, here, this next one here, let me box because these are kind of busy. But if I look at this one, this is look at me. That's hydrogen again, silly man. Okay, look here. So right here is helium. Now notice that the x-axis is in the same direction. It's starting at 1,000 millijoules per mole, and it's working its way across. But notice that these two electrons, now, the height over there is 2, so there's 2 electrons present, has actually moved a little bit closer to, like I wrote over there, the nucleus. It actually requires a little bit more energy to remove either of those 2 electrons. Well, why would that be? I mean, why would helium's amount of energy to remove 2 electrons instead of 1 on hydrogen be so great? Well, what we have to overcome is that force of attraction through Coulomb's law, right? So what we've changed in the numerator of Coulomb's law, and this happens for subsequent elements as we go through the periodic table, F, K, Q, 1, Q2 over R squared. The distance to them hasn't really changed very much as we're still in the first energy level. But what has changed is there are 2 protons in the nucleus. So if you think about those electrons, they now have a positive 2 charge pulling on them instead of a positive 1 charge. That means that this force value over here is going to be larger. As that nucleus gets larger, the force gets larger. Now we're in the same energy level, and that's true pretty much across individual energy levels. There are some small exceptions, which we talked about last year, and we'll see that in terms of ionization energy, and I'll try to explain some to you. But for the most part, The trend is as they get larger, as they get more protons in the nucleus, not larger, but within the same energy level, more protons in the nucleus, they're going to have a stronger force of attraction. And we will see that exhibited on that x-axis for the energy values necessary to remove them. Sorry, I'm so excited about this. All right. So let's skip ahead and go look at some other ones for something a little bit further down. So let's look at beryllium. That's not that much further down, but it is in the second energy level. So let's look at beryllium right here. So if you look at beryllium, look, I mean, it's got two different energy levels. It's got the first energy level and the second energy level, and there are 2 electrons in each one of those. So if I look here, I've got 2 electrons. This is 2 electrons and 2 electrons for that second peak. If I'm thinking about this in terms of where the nucleus is, right, relative to these electrons, which this is not right, but it's kind of easy to explain this way. If that's my nucleus, the first electrons that I hit are going to be in the first energy level, and there are 2 of them. That will be my 1s2. If I go to my second peak, those require quite a bit less energy to remove. Those are going to be the outermost electrons here, my valence electrons. That would be 2s2. Oh no. That's not beryllium. Oh, it is beryllium, sorry. Yeah, so there you go. So you could write an electron configuration from this chart, this PES graph. Let's do one that's a little bit more difficult. And notice that as I get closer to the nucleus, as the energy levels are closer, that amount of energy to remove those electrons is greater. Those are core electrons. The ones on the outside that require so much less energy, those are going to be your outermost, larger distance in the denominator, your valence electrons. Okay, so let's skip ahead, and we've got all of them listed here. Let's go look at sodium. I like sodium. So here's sodium. Again, look for the one with the highest values that are to be removed. That's going to be the electrons that are closest to the nucleus. Now, it is possible that they give you a graph that starts, say, boom, and they don't give you any of that. They start at a certain point, and you got to kind of figure out what it is. It's kind of weird and difficult. We'll practice a little of that later, but it might not be sodium that you're looking at, but it might be something in that entire first, group or family on the periodic table, which is interesting. Maybe in your homework. So here, if I look at this and say, okay, my nucleus is the ones closest to the nucleus, my core electrons are going to have the highest value. So this would be my 1s, and then there are 2 electrons, 2 electrons going across there. The next one, of course, would be my 2s, and there are 2 electrons going across there. What do you think that next little section is there, if you can remember electron configurations, though we have not really practiced them yet? It's got 6 electrons in it, and if you said it out loud or just waited for me to say it, you're right, it's the 2p. So that would be the 2p, and there are 6 electrons. Oh my goodness, look at that. And then the last one requiring the least amount of energy, and if you notice, this is not a lot of energy to remove this electron. Even though sodium has 11 protons in the nucleus, now you have this electron that is easier to remove than it was with the hydrogen atom. Its distance from the nucleus is far less. This would be that 3s1 electron. And because it is held so loosely, this is one of the reasons that sodium actually forms that +1 ion, loses that electron readily. Interesting. Okay, so I think at this point we can kind of go and do a couple of little examples and see how you do. So let's practice. So it says here, what element is represented by this? Now, this does not look like the other ones. Instead of having a y-axis, they've actually got the number of electrons just labeled at the top of each peak. Also look at the x-axis, it has been flipped. It's starting at 0 and working its way to 10. And the units here are electron volts. That's really irrelevant. We're just looking at the magnitude of them, not necessarily their units. What do you think? Which way should we start from? Well, I say we start with the one that's the highest. So my nucleus would be over here on this side, right? Those would be the ones closest to it. Those would be your core electrons. I see 2 of them. That must be the 1s, and there are 2. Look at the next one. That would be the 2s, and there is 1 electron. So what element do you think this is? If you were looking at a periodic table, 3 electrons, 1s2, 2s1, scroll over in your periodic table and you find it is lithium. If you're able to do that without me, or you pressed pause, which I probably should have told you to do, I'll do that on the next one. You should have gotten lithium. Proud of you. Good job. Okay. So look at the next one. This one here's got kind of some funky stuff going on with breaks so that we can have a, not have an immensely long independent or x-axis. But go ahead and try this one without me. I'll just sit here. You push pause and I'll come back on. Okay, so you finish pushing pause, I guess. So let's do this one. So the one that is closest to the nucleus is going to have the most energy to remove. Those would be your core electrons. It looks to me like this is that first peak over here. So this would be my 1s, and it would have 2 electrons. Now, here we're not given a y-axis. It just says number of electrons. So you're going to kind of have to look at the rest of the graph and determine what you think. If I go all the way over there to the right, all the way over here to the right, notice that that peak isn't as high as the others. That's probably a single electron peak, which, yeah, it is. So if I go through here, I've got the 1s2, and then the second energy level has an s, and the second energy level has a p. Well, that's a p6. And then I'm going to go to the 3s, and there are 2, and then the 3p, and there are 6, and then the next would be my 4s, and there is a 1. That's what you should have gotten. Did you pick which element it is? There they are. So the top one was lithium, like we did, and the bottom one is potassium. Pretty easy. Now look at both of those, one on top of the other. Look at the actual x-axis and the y-axis. They're different. There are lots of different ways that you can see these PES representations. So know what you're doing when you look at the graph. Think about what you're seeing before you just run out there and just write some 1s2, 2s2, 2p6 stuff. All right, let's do another one. So this one here, again, put this one on pause, but read the little note on the bottom and see if you can figure it out. You didn't push pause, and then come back and tell me, or watch me. Okay, so let's try another one. So this one, they said that the 1s peak is removed. So if the 1s peak is removed, my first peak is going to be a 2s. So I look for the side that has the most amount of energy. That's over here, so I'm looking this way out. They said the 1s peak was removed, so I'm starting with 2s. And it looks like, from the size of these, it's probably 2 electrons. The next one would be my 2p, and it's about 3 times the height of that one, so it's 6 electrons. And also all the way across, it's consistent. The next one would be 3s2, and then 3p6, and then, wow, what comes after 3p6 if you scroll across your periodic table? It's the 4s2. So here would be my 4s2. Oh, that's a terrible 4. Terrible 2, too. 4s2. Then you actually go across your Ds, but it's 1 energy level closer. They're actually added as core electrons rather than valence electrons. So that is my 3D, and its value would be 10, because I still have another peak. I must have gotten all the way through the Ds. And that last one would be my 4p6. Interesting, yeah? Not sure you were able to do that one, but if you were, applause. Let's go do another one. So, and that one, I'm sorry, I should have told you, that one's krypton. Krypton. All right. So here, last one. Press pause. Give it a shot. Come back in a second. Okay, you're back. So this one, again, they all look a little bit different. This one's got peaks kind of right on where the measured values are, instead of having a graded scale and you had to figure where they were or whatever. So at 208, you have that first peak. That is the one that requires the most energy. That's going to be the core electrons, or the beginning of them. That will be your 1s2 and your 2s2 and your 2p6 and your 3s2. And then next would be 3p, and it looks like it's a little bit higher, maybe half the distance higher. So that would be 3p3. And well, let's see. Let me just look. Yeah, it's phosphorus. I was going to say phosphorus, but I didn't want to make a fool of myself. So yeah, it's phosphorus. That's PES. I think we're going to have a little activity for you guys to do in the notes section or on one of the days in this unit. So look out for that. But love PES. There's no reason for you guys to get this wrong. And it does a wonderful job of explaining things in terms of Coulomb's law relative to your electron configurations. So periodic trends. We're going to do a little bit about periodic trends and talk about it. But the Aufbau principle is protons are added to the nucleus one by one. To satisfy that Coulombic attraction for those, they enter of course, as core electrons first. So they enter with the lowest energy level first. So you start with the 1s and you go to the 2s and then the 2p and so forth. And if you were to go across that periodic table, we've done this lots before, that's just the principle that describes this, they go in the lowest energy level and you work your way across. And then it goes through the 3D and the 4p like we saw a minute ago. In its ground state, atoms have electrons in the lowest energy level, and then you work your way across like I just told you. So let's go look at a couple of these together. Well, maybe not quite yet. Hund's rule, all orbitals in a sublevel must be half filled. So that's one in a p, another in a p, another in another p. And then you go back and you give parallel spins, or you go back and refill them. So it'll be one in the px, one in the py, one in the pz axis. And then you go back and you pair them up. If you look down here on the bottom, these are what are called orbital diagrams. But in an orbital diagram here, we can see that in terms of nitrogen, right there, we've got a single electron in a 2p, a single electron in another 2p, and then in the third 2p. And then if you go down, say, to neon, you'll see that they're all paired up. You pair them up one at a time. Been through this before. Okay. So let's practice an electron configuration. It has been a while since you've done these, even though I've been kind of just spouting them off like you knew what you were doing here through this PowerPoint. Oh, where did it go? Oh, I meant to have a periodic table here. Let's see if I can go back and grab a periodic table real quickly. I think I uploaded the wrong image, guys. I apologize. This one will work. So let's use this periodic table right here. So, oh, I forgot which one it was. But let's go do it and just do one electron. Let's not do that. Let me hit pause and see if I can fix this real quick. Okay, so I think I got it figured out. All right, so we're going to go do a couple of electron configurations. Let's do manganese first. So I put a periodic table in here. I just uploaded the wrong file, but okay. So manganese is located right there, element 25. And so what we're going to do is write the electron configuration from it. We'll do the full electron configuration, but you guys are more than welcome to write the shorthand notation if you remember how. I'll do both and then turn you loose for the other two, and then we'll come back together. So writing the electron configuration for manganese, what you do, the way I do it is I go across the periodic table, and this is the S block over here, of course the P block over here, the D block over here, which will be the energy level -1 for those. And down here in the bottom is the F block, and the F block is the energy level, of course, -2. Just as a reminder. So we're going to go through and get to manganese and perhaps talk about some charged species as well. But okay, so back to manganese. So what I'm going to do is go across. So I've got my 1s, and I'm going through both of these. So that would be my 1s2. Don't forget to write it as a superscript, not a subscript like a lot of guys did last year. Superscript 1s2, representing those two electrons. And then I'm going through this S block here, which is 2, energy level 2, S2. I'm going to go across second energy level of the P's, 2p6. Then I'm going to 3s2, and I'm going to 3p6. And then 4 through the S block, 4s2. And then it's n -1 for the D's. So this is the fourth energy level going across. This would be the 3D, and it's going to go 1, 2, 3, 4, fifth one, 3D, 5. Now you'll notice that that is correct. This is the right electron configuration for manganese in its ground state. However, you'll notice that the energy level goes 1, 2, 2, 3, 3, 4, back down to 3. You guys may see this often with that 3D5 written before the 4s2. So you'll see at the end of it 3D5 instead of 4s2. This is completely okay. They're listed in increasing energy level. But you got to be careful, because you'll think, oh, if I'm trying to identify an element here, I would just say, oh, it's calcium because it's 4s2. It's not. Make sure you look at all of them to determine if it's a full orbital or not. So it's full, all the d orbitals are filled, or if all the s orbitals are filled. And in this case, the d's are not. All right, so good. So that would be manganese, and I would write that, right up there in the blank, boo, manganese. But let me erase this. And we're going to go do shorthand notation for manganese and save ourselves some time. So here's manganese, element 25 again. And what I'm going to do is work my way backwards on the periodic table, backwards to the nearest noble gas. Don't go forwards, because we don't have 36 protons. We've got 25, so we got to find something with fewer protons, more representative of the core of this element or atom. So here I've got argon, it's got 18, so I'm going to write argon as a noble gas in brackets, which represents the electron configuration up to that point, which is super stable. And those are core electrons. So then I'm going argon, and then I just go beyond that. So argon, and then this is, of course, still the 4s, the fourth energy level. That would be 4s2. And then I'm going to step back down to the 3d, and I'll do 1, 2, 3, 4, 5. And there we go. The valence electrons here are those 2 electrons that are in the 4s2. This is a little bit of review, just a quick, because I'm here and, you know, I'm thinking about it. But if I had Mn2+, a lot of people like to remove those 2 electrons from the d orbital. They know to remove electrons and not add them because it's positively charged, but they remove them from something that is not valence. They need to be removed from the outermost electrons. So it's going to remove these 4s electrons, and for manganese it would be argon, or Mn2+ anyway, the manganese ion would be argon 3d5. Very common mistake. Even at the AP level, students make this mistake. You got to stop doing that. Okay, that's why I'm here, I guess. All right, so you can write either, it doesn't matter to me, in those blanks up there, the long or shorthand notation. When it's a long notation, they typically say the entire ground state electron configuration. But if you're just asked to write an electron configuration, you may write it in shorthand notation. Okay, so hit pause. I'm gonna come right back in a second, but go ahead and give those a shot. Okay, so I'm back. If you did all of these, you notice that chlorine is actually the chloride ion. So it's going to gain an electron. And so what you should have written, there's my periodic table I forgot earlier, was something like this. Now, if you had written this in shorthand notation, that's one thing. But this chlorine down at the bottom, this 1s2, 2s2, 2p6, 3s2, 3p6, that's great. But if you wanted to write it in terms of shorthand notation, a lot of students ask, oh, well, is it okay if we just, I believe it's argon, right? Yeah, it's argon. You would just, couldn't I just write argon in brackets? It's not really correct. I mean, it's kind of cheesy to do that. What you really want to demonstrate is that the valence is full without saying, oh, it's just argon. It's not argon. It has the same electron configuration as argon, but it might actually be more appropriate to write neon and then show your valence electrons. It won't take that long to show the previous noble gas and that you added an electron to make it the chloride ion. But if you wrote 3p5, you wrote for the atom, not the anion, chloride. So be careful there. You had to add an electron. And then the other ones, if you did shorthand notation, just pay attention to the ends. They're written as you would see them. So for this one, the ones that you would have written after the noble gas would be the 5s2 through the 5p2. There are exceptions, and in AP, the exceptions are going to be the same as pre-AP. Nothing new for you guys. It's going to be the copper and chromium families. And if you look, or if you remember, if they are near filling in the Ds, where you have one in each one except for the last one. So for instance, where are we looking at? Oh, it's not there. So let's go ahead and look, say, at chromium. Looking at an orbital diagram that I guess I'm going to kind of draw off to the side here. At an orbital diagram, so let's say this is the 4s orbital, and then I have 5d orbitals down here. So this would be my 3d, and there are 5 orbitals there. I would have 2 electrons in the 4s, and then if I went all the way to and assigned them naturally, normally, without exception, I would do this for chromium. I would assign those those 6 electrons that come after the noble gas this way. But this isn't how it behaves. It is actually more stable to have all of those orbitals half filled rather than have the 4s filled and the 3d have one empty orbital. So this electron here will actually be found over here. So you would have to delete it from here, and it would be set up this way. And so that's why it's drawn that way in the circled bit up here at the top, this up here. So it will actually half fill. The exact same thing happens in copper. So in copper, what happens is, well, a very similar thing, let's say. In copper, a very similar thing happens where you have your 4s2, but down here you have all but 1 electron present. So you have 3d9. It is more stable for that electron to drop down and be placed here, just like it was, very similar to chromium, and then the 4s would be 1. So just be careful. that when you're doing anything in those families, be it copper or be chromium, and the elements that are below them, molybdenum, and then the other one is gold, and so forth. If we look down through chromium, it would be this family here, and for copper, it would be this family here. Really, that's just the top three going down in there. But these three here would behave similarly. Those are the only exceptions that we're really holding you accountable for. So the same as we did in Prepe. Just know that if they're half filled except for one, that will drop down out of the 4s. And if they're completely filled except for one, in case of copper or silver or gold, that it is more stable with that single electron. Okay, so that's gonna be quits for today. I am going to see you guys in the next video. Hope that went well. See you soon.